Today's lesson is section 2.3, where we'll be calculating limits using the limit laws. So here we have a few basic ones. So if you have two limits of two different functions, but we're approaching the same value, we have several different properties that we can kind of deal with. So if we're adding two functions, taking the same limit, we can separate them by addition. Same thing for subtraction. If there is a constant in front of your function, you can factor that out and put it in front of the limit and just look at the function. If two functions are multiplied to each other, you can separate them by multiplication. If you have ones that are dividing by each other, you can separate them by division, just as long as the bottom or the denominator function is not equal to 0. If you have a function to a power, you can just take the limit of the function and then take the power afterwards. If you have a function or a limit of a constant, the constant is the limit. If you have a limit of a variable, it's really just you plugging in that approaching value to plug in. So if you have a limit to something to a certain power, then it's really just you plugging in that approaching value in for the x to get that value. Same thing for a radical, just as long as it's if it's a positive one, you get the don't get any negative values underneath the radical. Same thing with the last one there. If you have a function with a radical entirely over it, you can put the limit of just the function on the inside and then deal with the radical afterwards. And so there's a lot of nice nifty things that we deal with when we're looking at limit laws that make finding our limits a lot easier. Okay, so here what we're kind of doing is we're breaking things up. Now, I didn't go all the way out for this. Here I could have broken it up even further, but sometimes it gets a little redundant. So I know that you can kind of figure this out as well. So I separated it by subtraction and addition. I could have separated the 2 and the x squared and the 3 and the x and made them their own thing, and then also the power. But really, it's just a matter of separating them out and plugging them in. Same thing with letter B. There's division there, so I can separate the division out. But I could also separated the 2x squared out and the 3x from each other. But I did separate them out by addition, subtraction, just by the terms, the individual monomial terms. And I can only do that because we're all approaching the same value. If you had two that were, one was going to 3, one was going to -4, you couldn't do the same thing. But as you can see, letter A, the answer is 39. And here for letter B, we should get some 8s in the numerator to cancel out. And the bottom denominator looks like it'll be 11. So we get -1/11 for our answer. Okay, here's some more examples. Now, as you can see, we could just plug these in. So let's try that with the first one here and see that I actually get 0 over 0, which is undefined. But sometimes direct substitution doesn't always work nice and neatly like it should. So I can do other things that we have at our disposal, like algebraic, like factoring. So I can factor the numerator, which is difference of squares, which I get x minus 1, x plus 1, and so the numerator and denominator actually cancel out, leaving me with x plus 1 over 1. And now I can use direct substitution to get a value of 2 for my limit. Letter B, here I have the value of h in the denominator, so if I plugged in 0 right now, I would not get an actual limit, it'd be undefined. So I need to do some simplification with the numerator. It looks like the 9's cancel out. And both the terms at the top have an h in common, so we can divide out an h. It leaves us with 6 plus h. And so now I'm able to plug in that 0 to get a limit of 6. C, we have to do something a little bit different, kind of like rationalizing the denominator. But here in limits, we actually rationalize the numerator for these. So I'm trying to get rid of the t squared on the bottom, so kind of moving the radical to the bottom in a way actually helps us find the limit of this function. So notice I multiply the first, outside, inside. The inside and outside cancel each other out. And then I get rid of the radical on the first one. And then notice that I can get rid of the 9's at the top. And then that actually allows me to get rid of the t squares on the top and the bottom. So now I can actually plug in that value of 0 for t. And then once I'm able to do that, I will get 0 plus 9 in that radical, which is square root of 9, which is 3, and then 3 plus 3 in the denominator gets me 6. So then my limit would be 1/6. And so using those kind of ideas will help me kind of be able to finagle this around. Now I have to make sure that both sides are going to the same, approaching the same value for a limit to exist. So notice example 3, we have the limit of the absolute value of x divided by x approaching 0. Now numerically plugging it in, we get undefined, but I want to check this by graphing it. And so notice that here on the top, I'm approaching 1 from the right side of 0, and I'm approaching -1 from the left for this graph. And so those two do not equal, like we talked about in earlier sections, so that means it does not exist. Now the last thing we'll talk about here is something called the squeeze function. And so here you may have a function that direct substitution, and even looking at the graph, it's hard to pinpoint what your limit is approaching. And so we use something called the squeeze function to help us kind of determine what that is. And the squeeze function says that if you can figure out the limit of two functions, that one is less than your function and one that's greater than your function, and they kind of both have the same limit at that same point, then if that middle one has to be in between them, like inequality wise, then their limit must be the same at that same point regardless, because you're kind of squeezing that function in between the two, because they kind of are forced to all be the same thing at that spot. So an example of that here, we're going to use the limit of x squared sine of 1 over x is supposed to equal 0 as we approach 0. So let's say just graphing sine of 1 over x, it does a lot of like oscillating back and forth really quickly at 0, but we do know that sine of 1 over x is in between 1 and -1. So let's say our f of x is -1 and our h of x is 1. And so I do need that x squared, so I'm going to multiply all sides of my compound inequality by x squared. And so that gives me the following inequality. And so now I'm going to attach my limits to everything. And now if you look at the graph on the bottom there, as the limit of -x squared is approaching 0, we are approaching 0 for a y value because our vertex is 0 there. Same thing for limit of x squared is 0. And so because they're both 0 at that point, that means that because we know x squared sine of 1 over x is in between the two, it also has to be 0 at the same spot. Okay, have fun.